Okay, here are a few examples on chapter 1. Some of them are from the suggested homework problems that I put on the class website, and some other random problems. So I had asked you to do all the concept questions. I realized they're like 40 or 50 concept questions, but I think it's worth it to try each one of them. And even if you don't know the answer, it pays, I think, to try to think about the problem or the question posed, and maybe ask questions about it during class time. We'll in the chat. We'll ask your friends, and discuss the idea and the correct answers, and if you find them, and the implications. So I've listed here a few questions that I selected randomly from the concept, some of the concept questions, maybe not from all the sections, maybe overloaded with the first couple of sections of the book. But let's have a couple of examples. For example, when it asks what is the difference between classical and statistical approaches in thermodynamics, we talked about this in class, and we said the statistical approach to thermodynamics looks at individual atoms or molecules and the way they interact with each other, the way they have individual kinetic energy and rules. You cannot track every single atom and every single interactions, of course. So you work in terms of average quantities. So the average for these group of molecules or particles is this, and it goes up and down, and you work with distributions like probability distributions and whatnot. But in this course, like I said, we are dealing with classical thermodynamics, where the continuum assumption is in effect. The continuum assumptions, the thing is one continuous piece of matter, like a gel or jelly, that even if you go down deep microscopically, you wouldn't notice any particles. So talk about density. It's a uniform density within the locally. You don't go from an atom to a vacuum between the atom and the next atom, and then to the next atom, and so on. I think we talked about this plenty in the lecture notes. Then another question is, why does a bicycle or a bicyclist pick up speed on a downhill road even when he or she is not paddling? Does this violate the conservation of energy? لا طبعا، لأن downhill, so he is losing some. This is the bicycle. I can't draw a bicycle. He's losing potential energy, and this potential energy is continuously losing potential energy. So this guy with respect to time is zero. So when you take the kinetic energy, the other side of the equation, this will be positive. So this will be negative, and this will be positive on the same side, so that the energy is conserved. So this is a continuous change in the form of the energy from potential energy to kinetic energy. Relate that to the rock falling problem. We said it has maximum potential energy, and as it falls, some of the potential energy is converted to kinetic energy. And just think about what happens when it hits the ground, تدحرج شوية, and where does this energy go? So think about this in terms of extension to this question. An officer worker claims that a cup of cold coffee on his table, warmed up to 80 degrees Celsius by picking up energy from the surrounding air, which is at 25 degrees Celsius. Is there any truth to his claim? Does this process violate any thermodynamic law? Well, assuming the amount of energy picked up is the same, meaning he picked up for example 12 kilojoules and then or 12 joules or 100 joules, and this environment, the surrounding lost 100 or 12 joules, exactly the same, the first law might be okay, ولكن we all know in the processes have a certain direction in nature, so this is impossible and it violates the second law of thermodynamics. You will see so many of these questions and so many of these phenomena and claims actually during your lifetime. There used to be more, like 100 years ago, بس الناس استفادوا من thermodynamics and they benefited from 100 years of engineering, and they stopped believing these type of claims. So one of the most amusing things a person can experience is that in a certain part of the world, a car on neutral going uphill when its brakes are released. So نبوش السيارة and it just goes uphill when it's on neutral. So such occurrences are even broadcast on TV. So can this really happen, or is it just some bad eyesight? How can you verify this road is real? في L زايدة uphill or downhill. You could طبعا they could fool you with slanted buildings, ولكن في الحقيقة ممكن يكون downhill والbuildings are even slanted more, and they slant, I think. So, but we know from our studies and from nature, from our common sense, that this is impossible. Okay, so more bad eyesight is like a gimmick, a trick, a camera trick. So we'll see a few of these things. How can you verify uphill or downhill? They have في شيء اسمه I forgot what it's called. في عندك bubble ومسطرة كذي, and you lay it horizontally on a surface, and the bubble, you watch the bubble goes up or down, and if it stays in the center, then this is level. They use it المساحين والfinishing for flooring in masons, يعني الbuilders المقاولين والعمال البناؤون. The specific weight of a system is defined as the weight per unit volume. Okay, so weight اللي هو mg per unit volume. Okay, this is the specific weight اللي هي هذه. Note that this definition violates the normal specific property naming convention. Is the specific weight an extensive or intensive property? ليش violation of the naming convention مع specific؟ لما نقول specific, usually we say like internal energy specific, I mean internal energy per unit mass. لما نقول volume, specific volume is volume per unit mass. So when I say specific weight, شنو الweight mg per unit mass فيصير g. فلا مو هذا. This is not what we mean by the specific volume. I mean specific weight. So when we specific weight شوية نعطل الدefinition, the naming convention اللي اتفقنا عليه, specific something, specific whatever. So this is نوعا ما violates. Yes. Is the specific weight an extensive or intensive property? Let's look at specific weight. Specific weight is mg over v. This guy m over v is nothing but rho. Actually, specific weight, we call it rho g when we use it in manometers, for example. And this is a constant. And this is intensive or extensive? You could say in 1 over rho is just v, اللي هي specific volume, and this is an intensive property. So basically, specific weight is an intensive property. I don't know if this is good enough for you, but this is how I think about it. For a system to be in thermodynamic equilibrium, do the temperature and the pressure have to be the same everywhere? Yes. في حين البريشر في نظر. So the temperature واحد الاشياء thermodynamic equilibrium قلنا charge equilibrium, chemical equilibrium, etc. وفي thermal equilibrium in the temperature all the way the same, and mechanical equilibrium the pressure has to be all the same. So if you have هني ما يصير مثلا piston cylinder device and it's pushing this, ما يصير هني البريشر is مثلا 100 kilopascal وهني 50 kilopascal. So the pressure نوعا ما has to be the same. The only exception اللي يعني الاسterisk الملاحظة البسيطة that you have to take into account in some for example الاتموسفير. When you have an atmosphere في air here is dense لأن it has many layers of air on top of it, and في at the higher atmosphere طبقات الجو العليا the air is thinner, much thinner, so less dense, but it's sitting on layers of more dense or denser air. So you can say they are in equilibrium ولو ان the pressure is not totally the same. Okay, but then again we rarely have a system that extends this high into the atmosphere. So basically, yes, they have to be the same everywhere. It's safe to answer this way. What is the quasi-equilibrium process? What's important? Why is it important in engineering? What is its importance in engineering? An awkward way to ask a question. طبعا quasi-equilibrium process is a process where the intermediate states are all يعني from one equilibrium state to another equilibrium state and so on. So the difference between them is infinitesimally small, متناهي في الصغر. What is this important engineering? This is without this you lose track of the system. You cannot define a state and يختفي مكان ويطلع مكان ثاني. You cannot just lose your system and all its properties and it shows up suddenly at the other end of the process. So you have to keep track of your properties, and you have to have well-defined properties and well-defined systems throughout the process. Okay. I hope it's a good enough answer. I hope it's a correct answer. Define isothermal, isobaric, isochoric process. You know this where the temperature stays constant, isobaric, when the barometer, so the pressure stays constant, and isochoric or isometric process is where the specific volume stays constant. Sometimes the volume stays constant. So let's stick to specific volume. بما أن هذا intensive, let's say specific volume stays constant. Okay, so T, P, or V. Yeah. We'll see بعدين isentropic يعني ال S stays constant. S1 is equal to S2 اللي هي entropy. We'll see in chapter 7. So what is the state postulate? We said you should memorize these and after you understand them fully, and the state of a system, simple compressible system, we talked about why we say simple homogeneous compressible, and the pressure has an effect. Okay, it's not هذا يتغير the pressure as it changes as it wants, and this one is the system is totally ignoring your pressure. So we specify a simple compressible system. The state of it is completely specified by two independent intensive properties, and we talked about what it means to be independent and what it means for a property to be intensive. Okay, and two, you know what two is. Finally, the pressure of in a compressed air state. Okay, so the pressure in a compressed air storage tank is 1500 kilopascal. What is the tank's pressure in kilonewton and meter units? We know 1 pascal is Newton meter. So if I say مثلا 1500 kilopascal, and I'll say I'll multiply this by this this is 1 kilopascal is 1 kilonewton meter. So I need to do it in kilonewton بس خلاص. So 1500 kilonewton meter. Sorry, my bad. So joule هذا. So 1 kilopascal أو 1500 kilopascal. الباسكال الواحد أضربه بشنو؟ kilopascal. Let's take it 1 kilopascal is 1000 pascal if you want, and then أيضا نضربه شنو 1 ما له داعي. So 1 kilopascal وهذا 1 kilonewton per meter square. So I'll just 1500 kilopascal, 1500 kilonewton per meter square. That's pressure. So force per unit area. Well, that's it. If I had told you in Newton, you would have to multiply. So 1,500,000 Newton per meter square. Oh, kilogram per meter. I'll just kilonewton. So 1500 kilonewton per meter square, and we know in kilonewton 1 kilonewton is 1000 newton, and 1 newton is 1 kilogram per meter. I mean kilogram meter per second square. So this is what you want: kilogram meter second square, and kilogram kilometer per second square. You just multiply 1 meter هنا meter فوق هني, so 1 meter هني أو 0.01 kilometers. So بالنهاية يطلع 1000 نفس الشيء شكله. Okay, so do these and the others. Let's look at a couple of manometer problems. I don't know how I'm doing on time. We have this manometer problem where the water in a tank is pressurized by air. And the pressure is measured by a multi-fluid manometer. So you have one fluid, another fluid, a third fluid, maybe a fourth and a fifth and a sixth. So it doesn't matter. As shown in the figure. So determine the gauge pressure of air in the tank if H1 is equal to 0.2 H2 هذه الأطوال H1 و H2 و H3 is 0.46 meter. Take the density of water, oil and mercury to be 1850 and 13,600 kilogram meter cubed respectively. So we have water here and oil here and mercury here. Like I said, you will have so many people giving you so many advice and tricks and procedures and ways to do these problems. You want to determine the gauge pressure of air. You have to ask yourself, هل air wants pressure هنا or here or here or here or here? If you want the pressure here or in the middle, you have to make a decision. You want to consider the density or the weight of air. If not, then the pressure here is the same as anywhere here. So I'll take it as the pressure at the surface. So the pressure at, let's call this pressure tank. Okay, I will adjust the pressure. My guess in the pressure here is just the pressure, the atmospheric pressure. Okay, I'm saying in the pressure here is the atmospheric pressure, but this is clearly wrong. And the pressure here is much higher than or much lower than the atmospheric pressure. So the pressure here is atmospheric pressure. If I go down into this fluid, into this mercury, I'm carrying above my head some amount of fluid. So what is the weight of this column of fluid? طبعا I'll work in pressures. I'll just multiply forces and multiply the area. Everything is for the area. So I'm assuming this is a constant area throughout the cross-sectional area. So this is basically the pressure. So I'm adding this on top of the pressure. So it's not only P atmospheric, ولكن additionally this is oil, هذا mercury. So Hg وبعدين H. عدل. So rho GH. Let's spell it out. So this is rho Hg G and then H. So this is meter per second square, and this is kilogram per meter cubed. So basically راح يصير this will be kilogram meter per second square divided by meters square. So this is Pascal. And then you will notice an atmospheric pressure is not given, so the gauge pressure. So you want the gauge pressure. Okay, so atmospheric pressure and then rho Hg G H1 and then H3, sorry. And then the pressure here at this point is the same as, well, it increases and then it decreases once you go up, and then it reaches this pressure. So the pressure here is the same as the pressure here. But then as you go up in the pipe, you leave some material below you. So until you reach this point. Okay. So this point, the height of this column that you left behind you is no longer on your head. So this is rho, this is oil, GH2. Okay, so this is a minus sign to relieve you of this weight, and then the pressure here is the same as the pressure here, and then you want the pressure, and then increases the pressure because you're putting more on your head, and then decreases, then this is the same as this pressure, and then it decreases because you're leaving some of the water here below you. So this is minus rho H2O G H1. Okay, you have to pay attention to the units. أول شيء you have to pay attention to the gauge. So the gauge is the pressure minus P atmospheric pressure. So this is the difference. The pressure above the atmospheric pressure. And this is P gauge. Okay, this is equal to this. You substitute, you know all the G's, and you know all the H's, and you know all the densities. This rho GH will give you, if you compute it, this is kilogram per meter cubed with meter per second square, and then with meter. H is the meter. So this will give you Pascal. And اللي هو Newton per meter square. Well, Newton is just force, unit of force. So this is mass times acceleration. So kilogram per meter, kilogram meter per second squared. So this is the force, MA, and you're left with, this goes with this, which becomes 2. So you're left with Newton, okay, divided by meter squared. So this is Pascal. Okay, you have to be careful with this. This is just a Pascal. If you want to report it in kilopascal, you have to divide all of these. This is rho Hg G3 whatever plus divided by 1000 so that you get kilopascal. Otherwise, what you're getting here is Pascal. So this is an easy mistake, easy thing to miss. So don't miss it. Next, let's look at a problem, a related problem. So you're doing so you have the diameters of the pistons shown. So you have a piston, this piston and this piston. You have both diameters, the big and the small. So this is D1 and this is D2. Okay, and هذا أكبر شكله. So you want to determine the pressure in chamber 3. So هذه هني. You want the pressure here. In PSI absolute. So this is pounds or pounds جدي per square inch. So pound per square inch PSI, and the A is absolute. So you'll find PSI G and PSI A. So these are the English units, so British units, not the ISI units. Anyway, we want and these are given in inches. The idea here is to this is in equilibrium, so we know that the forces here, or pressure, mean forces. So you know that the forces here and the forces here are the same. And then, so if you do like a summation of forces in the y direction, and if this is stationary, this will be 0. So what is the summation of forces? Summation of forces in the y direction. This will be P. Force is nothing but P times the area. So you have this guy. You have any F1 and you have F2. So F2 and you have F3 ولكن just acting on this guy بس هذه. Okay, طبعا all around. So you'll say and I have a positive هني direction, so this is P1 A1 اللي هم معطينا اياه. شنو A1? This is pi over 4 D1 squared, and this is 150 طبعا PSI. وبعدين I have شنو اللي acting on the piston. Doesn't في acting in this direction, I don't care. في acting on the cylinder, which I don't care. I'm interested in the thing that acts downward هني, so this is negative. They will come up to be 0 anyway. So يعني summation. So this is P3 times شنو الاريا؟ الاريا عبارة عن الاريا هذه minus this area. So this is like area 1 minus area 2. And area 1 is طبعا this guy. Area 2 is this with a D2. And then you have this guy is also acting in the negative direction, so minus P2 area 2. Okay, so pi over 4 D2 squared, and so on. So you sum everything and you have the pressure in chamber 3, so this is unknown. Okay, this is known, this is known, this is unknown. And that's it. Okay, so when you're faced with a problem that you've never seen, as is the case, especially early on, and you have never studied it, and you don't recall any simple example from your book or from your problem sets, it's always a good idea to go back to the basics. What do I know? I know the summation of forces. I know that energy is conserved. I know that mass is conserved. Let me write out my mass conservation or the energy conservation, and see where the logical steps and the assumptions I make lead me. In order to do that, of course, you have to know what do you mean when you say En. How can energy get in and out? Well, can Q in or W in, phi mass in, ME in? Well, it depends on the type of system. And so you have to know these details, not only the abbreviated governing equation, but also the individual components and what they mean exactly. Now, so a vacuum gauge, let's look at this problem. So a vacuum gauge connected to a tank reads 15 kilopascal at a location where the barometric reading is 750 millimeter of mercury. So Barometric reading means this is some information about P atmospheric. I have information about this, ولكن not in the units that I'm most familiar with. It's not what I'm familiar with. But this is nonetheless the atmospheric pressure. So let's say P atmospheric in millimeter of mercury. And I have the vacuum. This is a vacuum gauge, and it gives me this. So you have P atmosphere. If you recall, if this is P atmospheric, and this is the absolute pressure, P absolute, then this guy is the P vacuum. Okay, it's positive, لأن it's defined as when the absolute pressure is lower than the atmospheric pressure, then this P gauge, P vacuum is equal to P atmospheric minus P absolute, and العكس صحيح, P gauge is equal to P absolute minus P atmospheric. الفرق اللي يصعد هذا P إذا كان هني معناتها this guy is P gauge, إذا كان الابسولوت تحت this guy is P vacuum. So we have a picture of this. So this tells me basically that the atmosphere, the absolute pressure, and then P vac is equal to 15 kilopascal. يعني it's below 15 kilopascal, below the atmospheric pressure. Okay, and you want to determine the absolute pressure in the tank, and you want to take this as the density of the mercury. Okay, it doesn't say. Oh, it says mercury. So basically, if you remember the barometer, it looks like this. So when I see the weight of this with length mala 750, I'm going to go back to the basics. This is 750 millimeter of mercury. Then I know the P atmospheric here, this is connected, so the pressure here is the same pressure here, so the P atmospheric is equal to this. Well, P atmospheric is the weight of this guy, of this column of mercury. So I know a P atmospheric is equal to rho mercury G H مع mercury. So this is rho معطيني 13590 9. وساعات يعطيك 9.81 ولا 9.807 ولا whatever ولا 9.9 في قعر الوادي, and this guy is 0.750. Okay, and this has to be in meter, and this is given in meter. So I have the atmospheric pressure. ولكن this guy will give me 13,000, يعني 13,500 times 10 almost راح يعطيني 135,000. okay, 135,000 أقل منه بشوية 0.3 هذا, so almost 100,000. okay, so 100,000 شكله بيصير شنو? If you work out the units, you'll find that this is in Pascal. So 100,000, so 100 kilopascal. This is your absolute pressure. عدل, this is your atmospheric pressure. عفوا, this is your atmospheric pressure. What you want is the absolute pressure, and the absolute pressure is P atmospheric minus P vacuum. So basically 100 minus 15 اللي معطيني اياها, so 85. So it starts with knowing what the barometer does and how to compute the atmospheric pressure from these readings, and just knowing the relation between the gauge pressure and the absolute pressure. The one thing I want to caution you about is units. So units will be the cause of you losing like 1/4 of the grades in this course probably, وخصوصا الكيلو باسكال والباسكال، and هذا gives you thing in Pascal. Okay, so another barometer problem. شكله سويت copy ورا بعض. The barometer of a mountain biker reads 930 millibars at the beginning of a hiking trip and 780 millibars. Well, 900 millibars is just millibars, يعني هذا مضروب by 1000, so this is bars, so this is 0.930. You multiply by 1000 you'll get 930, ولكن راح يصير millibars. So 0.93 bars or 0.78 bars at the end. So you want to neglect the effective altitude on the local gravitational acceleration. So G صدق انه صعد وايد 1000 متر يمكن 100 متر 200 متر. G is constant. We don't want to complicate things. On local gravitational acceleration, determine the vertical distance climbed just by looking at pressure. Assume an average air density of 1.2 kilogram per meter cube. So again, what you want to do is أول شيء convert this. So let's do this أسهل. So this is P pressure تحت 930 millibar is equal to 0.93. مو 0.93. This is 0.93 bars. So this is 93 kilopascal. وهذا 780 whatever راح يصير 78 kilopascal. So with these, the difference in pressure, the pressure is like we said هذه الأرض, and the atmospheric pressure هذا barometer measures atmospheric pressure. إذا هذه الأرض والخريطة كذي, if you put a column هني, this is the weight of the column of air. This is column. So column of air من هني إلى نهاية الأتموسفير. So usually the weight of the column of air, the pressure, is just the force divided by the area, is just rho g h, and h is the height that we want, and rho is the density that we want. ولكن we don't want the weight of the column of the air. هذول عندنا atmospheric pressure. We want the difference. So basically the difference in pressure is basically the rho اللي we take it to be constant, g and delta h اللي هو what we want. Notice in this guy will give you in Pascal, and you're expecting something in kilopascal. عدل؟ and هذا difference in kilopascal. So basically, يعني you could multiply this, you divide this by 1000, ولا you multiply this by 1000, 93,000 ولا 87,000. وبس basically delta P is equal to delta H divided by 1000. So you have this as delta P. شو الفرق بين هذا وهذا? This is 93 minus 86. So this is 15 kilopascal. Any 1.2 times 9.81 times H. We don't know what this is. We want vertical distance climbed divided by 1000. And that's it. Okay, should be huge actually. Change in 93 kilopascal إلى 87 kilopascal is serious. So let's look at piston cylinder devices. I don't know a gas is contained in a vertical frictionless. So لما يصعد ينزل على كيفه, there is no friction هني, يقاوم الشغل. So all the energy is basically when it expands, ليش يقول frictionless? When it expands, all the work, all the body work done is stored in this spring. Nothing is is spent as heat due to friction. Okay, nothing is lost to كheat. ممكن heat البستن، ممكن heat cylinder، ممكن heat outside، ممكن heat air هني، cylinder, spring, and so on. So we usually we make an effort to say frictionless. Be careful, يعني don't worry, nothing is wasted. So this gas is contained here, and the piston has a mass of 4 kilograms. This is not a weightless piston, so this is mg. So there is a force, downward force, الغاز. And pressure, يعني when you divide it by the area of the piston. And cross-sectional area of 35 centimeter square. So 35 من الحين أقول إن 35 centimeter square اللي هو 1 so اللي هو يعني 100 أقل اسم على 1 meter square. So this is 0.0035 meter square. So I add 4 zeros لأن هذا square. 100 2 zeros for each power. And this is 4 kilogram. So a compressed spring above the piston exerts a force of 60 Newton. So 60 Newton on the piston is done by the force is done by the spring. And if the atmospheric pressure is 95 kilopascal, determine the pressure inside the tank, inside the cylinder. So أعطاني atmospheric pressure, so that I want the absolute pressure inside the tank. So if you do like a summation of forces on this cylinder, you'll have this cylinder, you'll have F spring, okay, times the area مرة واحدة, and mg. Let's forget the area and do summation of forces. So sigma F, the y direction is 0. So I'm abbreviating this. So you'll have this guy, and you'll have F مال spring, and you'll have F اللي هو مال atmospheric pressure. So P ATM A مالت شنو ال A مالت البستن، A مالت البستن، okay. Cross sectional area مالت البستن. So multiply the atmospheric pressure, and then I'll have the P مالت الgas, just I'll call it P, times the area مالت البستن. Okay, yes, I think that's it. Atmospheric force, atmospheric pressure, force, weight, and the spring. So they're basically as such. So هذا يعادل هذا. بعد في شيء بس الويت، sorry الويت بعد. So this is mg. So كلهم اللي تحت، الوحيد اللي يقاوم, this is the only thing that's upward. So P A مالت البستن positive equals F spring plus P atmospheric AP plus mg. This guy, spring, I've been given 60 Newton. So if you want to, usually I'll give you displacement in chapter 2 or 3 or whatever, displacement, and you calculate this Fx displacement due to this force. في هالحالة I'm having 60 Newton, and if you are dealing with kilonewton and kilopascal, it's better to transfer this into 60 kilonewton. So I have to divide by 1000, and the atmospheric pressure is 95. So this is 95 times 95, just 95 by itself, and area is given, area. Sorry, this is, yeah, fine. And then mg is just a force, so this is 4 kilogram. 9.81. So this is the only, and this is, the pressure is not known and area is known. Okay. Oh, that's it. And this area is known as well. 95 times the area. This is known. So the only unknown is the P. You solve for it. Next, you have a problem that's similar to the manometer problem, ولكن فيها يعني some scary picture. There is no tank. What you want to calculate the absolute pressure P1, which is here. Okay, so at this surface, P1 is this surface. Let me change the color. P1 is this surface of the manometer shown in the figure in kilopascal. So you want this in kilopascal. Sometimes I'll tell you in Pascal, or in bars, or in millibars. So pay attention to this and bring it out to yourself early on. The local atmospheric pressure is 758 millimeter of mercury. We all know how to convert this. So if you want to if you convert this, or just memorize this in a 1 millimeter. So 1 millimeter of this is the unit of pressure. 1 millimeter is equal to 0.1333 kilopascal. Okay, so you could multiply this by this guy and you get it in kilopascal. So we converted this millimeter atmospheric pressure. So this is P atmospheric pressure is equal to 0.1333 times 758, etc. So you have this. ولكن you want P1. So again, my usual way of doing things, and P1 is equal to atmospheric pressure. ما عندي atmospheric pressure. So what I do, I'll apply atmospheric pressure. But this is wrong. I know it's wrong because it's more. Because as I go down, I'll increase the weight above my head. So I'm adding. Well, the pressure here is the same as the pressure here is the same as the pressure here. So I'm adding this guy. So this is rho fluid B, right? Fluid B, G, and then H, HB. All right, I'm here. And then as I go down, I move fluid on top of me until I reach here, and the thing is 5 centimeters. So this is minus rho A G H A, right? Yeah, I think. I wonder why they give this length. And هذا connected, these are the same. So I hope I'm not missing a thing. I hope I covered the whole thing. So this is the pressure at point 1. Okay.